I will talk now about elastic potential energy. Just take it. Now we need to remember that the work is equal to the change kinetic energy, which is equal to kinetic energy 2 minus kinetic energy 1. And the work is equal to the negative change. This is delta, means the change. The potential energy means U1 minus U2. We have a minus sign. And the mechanical energy is equal to the kinetic energy plus the potential energy. This potential energy sometimes plus any other work. If you remember from the books, we have a work jump from type to type of energy. We have a work from any other source. This potential energy may be just one shape as gravitational. Maybe it is the second shape we will deal with, which is the elastic. So the mechanical energy will be the kinetic energy plus the potential energy due gravity plus the potential energy due a spring force or elastic force. Here, the work is equal to F multiplied by X by cosine theta. We need to cheat from that when we solve the example. The kinetic energy is equal to half mv squared. The potential energy due gravity is equal to mg y. Y is the altitude due gravity. We need always to find our, or to assume our origin. Now we have the elastic potential energy. From before, we know that Hooke's force, which is equal to minus K multiplied by X. X is the compression distance for the spring. I will not derive the Hooke's or the elastic potential energy. It will be 1/2 K X squared. That's it. K is the same K, X squared is the same compression distance. That's it. So the potential energy due the spring is 1/2 K X squared. K is the spring constant. If the spring is light, it is easy to move it, then K is small. If the spring is need more force to push it or expand it, then K is big. Any question about this? We will start now for maybe a long example. But we will apply everything in that example. We will apply the kinetic energy, the potential energy, the mechanical energy. This is a comprehensive example. You can assume it as a review. Again, today we deal with the two quantities, new quantities in physics. Potential energy due gravity, potential energy due elastic, and the mechanical energy. Just our lectures, just quantities and applications. Now we talk about the elastic potential energy. Now we need to put an application. Before I forget, we know that this is a spring. It is a linear spring. We can push it, we can expand it. Also, we have this spring. We can push it and expand it, but rotationally in angle. The application on this spring, it is inside the clocks. Okay, you can see it sometimes if your clock is transparent, has transparent holes. Also, the wall in our house, when we rotate it, then it come back to its position. It contains a spring like that. In elevators, in the elevator well, this row, there is a spring downward because when the elevator go down, it will not be stopped by the ground. It will be stopped by a spring. You know that springs are always used in our life. It depends also. This spring, when we push this spring by a force, maybe this force, maybe this is our initial situation for the spring without any expansion or compression. We apply a force, maybe this force, it's a box, maybe it's a box with a weight mg downward. It will push the spring downward. If we remove this force, then the spring will expand again. And if there is anything here, if I push the spring here and I put some mass and I release it, then the mass will be released by a kinetic energy, by a velocity. Then we have kinetic energy. This kinetic energy, it's energy. From where it comes? It comes from the energy stored in the spring situation. The spring situation gives us a potential in it. We use this also in the bow. We have a string. When we pull it with this rope, a rope or something like that. When we release it, the potential energy from the elastic potential energy will be given to this rope to be as a kinetic energy because it has a velocity now. So the potential energy or the elastic potential energy is used many times in our life. Now I'll go again to the example. If we have this system, we don't have any frictional force. This is 0 point and the maximum altitude is 3 meters. So this is point number 1. Always we need to name the positions. This is point number 2. And we have a spring here. We have a point number 3 here. The spring, the mass. Initially, we have the mass at altitude y=3. We release it. Then it will start moving without friction. It will come to this track. It will come to the spring. It will push the spring. So we have a change in length. We have x. At this point, this is point 4. When the spring is pushed, okay? The spring has K. It is equal to how much? 120 newtons per meter, okay? The mass is equal to 5 kilograms. Small numbers, easy numbers, just to understand the physics. And Y at each point, how much y? y2 is equal to y3 is equal to y4. How much? It is 0 at the 0 level. Okay, what we need to find? Find U1, K1, mechanical energy, and find everything everywhere. And the spring compression. Find X also. Okay. At point number 1, just as we did in the building case. At point number 1, we have the mechanical energy. We don't need to name M1, M2, M3 because it is the same. Is equal to the kinetic energy at point number 1 plus the potential energy at point number 1, and this potential energy due gravity. So due gravity 1 plus we have another potential energy. Potential energy, elastic potential energy at point number 1. It is E. Okay. We don't have any other work. Work from other forces, for example, frictional force, we don't have. We just have free term. Okay. The mechanical energy is equal to the kinetic energy, 1/2. The mass is 5 again. The velocity, it was 0 squared. We don't have velocity there because V1 is equal to 0. It's a free fall. Plus the potential energy, mgh, mgy or h. H is the height. M is 5. G is 9.8. Y is a 3. Plus the elastic potential energy, it is 1/2. 120. How much the compression now? Initially, how much the compression? It is 0. We don't have any compression or expansion. This will be multiplied by 0. So the potential energy due to the spring is 0. The kinetic energy is 0. The mechanical energy will be equal to 0 plus this thing, which is equal to 147, which is a good number, plus 0. So the mechanical energy now is 147. It's always the same. We need to move this to the second point. At point number 2, we have the same relation, but at point number 2. So our mechanical energy is equal to 147, and it is equal to kinetic energy at point number 2 plus the potential energy mg2. How much is it here? How much the potential energy here? Can't tell me. It is mgy. How much y? It is 0. So it's right. 0. The potential energy due gravity is 0. Plus how much the potential energy due the spring? There's no compression. It is 0. So our kinetic energy here is equal totally to. So kinetic energy at the second point, it is equal to 147 joules. It's simple. What about point number 3? It is the same. Mechanical energy is equal to 147, which is equal to the potential kinetic energy at point number 3 plus the potential energy at point number 3. The altitude is 0, the same 0. How much the compression of the spring? It is 0. So it is 0 plus 0. This is 0 due gravity. This is 0 due elastic. Gravity, elastic. So the kinetic energy again at this point is the same. we don't have any loss of the velocity. We don't have any acceleration or deceleration because we don't have any friction force. Now, what about the fourth point? At the fourth point, the force pushed the spring the maximum push, the maximum distance. Then at maximum distance, remember the projectile motion at the maximum y, the velocity equal to 0. Remember that? At maximum distance. Here we have a maximum distance. What is the velocity at maximum distance? This is at point 4. The mechanical energy is still 147. Is equal to the kinetic energy, which is 1/2 5 V4 squared. Plus, how much the potential energy here? Due gravity. To 0. Gravity. We are the same altitude. What about the elastic potential energy? Okay, it is 1/2 K x squared. K is given. X, we don't know X how much, but we can find it. What is the velocity at this point? At the maximum point, the velocity is 0. After this pushing, the object will repel again to the opposite direction. But at the maximum distance, this is 0. So the kinetic energy 4 is equal to 0. So all of our mechanical energy is equal to the elastic potential energy. If you ask about the elastic potential energy, now it is equal to 147. What is the X? Yes, Alan. It's simple. I'll show you. Where is it? I'll put it here. U elastic is equal to 147, which is equal to, that is the relation. 1/2 120 x squared. So x is equal to the square root of something. This with this, it will be 60. It is 147 over 60. This will be equal to positive or negative. X, sometimes we expand the spring, it will be positive X. If we push it, it's a negative X. But in general, we need X. We don't care about positive or negative, but we can understand that the sign, the meaning of the sign. Okay? X in this case will be, it will be Aha. .495, I think, meters. It is 49 centimeters, just like this. The spring will be pushed like this. Maybe it is a long spring, and it will be pushed by 50, half a meter. So this is X. Positive or negative, I don't care, because I know the meaning of that. If I suppose this is the positive direction, then it is positive. If this is the negative direction, then it is the negative. It's okay. Any question about this example?